Welcome, Duke alumni, family, and friends, to this session of the Forever Learning Institute, an interdisciplinary educational program organized in a set of thematic courses. I'm Ann Stevenson, Director of Professional Development with Duke Alumni Engagement and Development. Thank you for joining our program today, The Power of the Future. This program is part of our theme, Energy Transformation, inspired by the Duke Climate Commitment. Today's program is the fourth and final session in the Energy Transformation series that will explore what energy is of the future may look like and what it will take to live in a future powered by sustainable emergent energies. Joining us today as host and moderator is Christy McCain. Christy is a graduate student at Duke University's Nicholas School of the Environment, where she is focusing on energy and the environment. Prior to her time at Duke, Christy worked in social impact investing, where she led investments in microfinance institutions and impact-focused banks in India and Southeast Asia, and investment banking, where she supported the origination of asset-backed securitization transactions for financial institutions. Christy will be joining an impact venture capitalist after graduation, where she'll be investing in companies driving sustainability and environmental impact in their lines of business. Welcome to the Forever Learning Institute, Christy.
Thank you, Anne, for the introduction, and welcome again to all of the alumni that have joined the call today. I'm really looking forward to a fascinating discussion around technological advancements to powering the clean energy transition. We have three speakers here with us today. First up, we will hear from Dr. Jay Liu. Jay is the George Barth Geller Distinguished Professor of Chemistry at Trinity, with areas of research including renewable produced and naturally occurring geologic hydrogen, also known as green and white hydrogen, respectively. After Jay, we're going to hear from Lincoln Pratzen, the Jindal Family Professor of Energy and Environment at the Nicholas School of the Environment, who will be sharing some of his research on developments in geothermal energy. We'll take an opportunity for Q&A surrounding these generation technologies after Lincoln's presentation, and then we'll move into a discussion on the much-needed grid and transmission modernization from Tyler Norris. Tyler is a PhD student at the Nicholas School of the Environment in Environmental Sciences and Policy. Again, please share any questions you have as we go in the chat. We will be monitoring that, and we'll try and get to all that we can during the time we have allotted. With that, I'll go ahead and pass it off to Jay to kick us off with advancements and opportunities in hydrogen.
I'm Jay Liu. I'm a professor in chemistry. I want to tell people today about hydrogen and carbon dioxide. This slide is not, everybody is familiar with this. We are talking about the relation between climate change and the consumption of fossil fuel. So an easy question to ask is, what should we do if we know there's such a good relation between the amount of fossil fuel we use and the temperature of the Earth? Easily, the answer is, can we stop using fossil fuels? It's not it's a simple question, but very difficult to answer because fossil fuels are used in many aspects of our daily lives, not only for energy, for driving cars. What are the alternatives from the energy point of view? We have solar, wind, wave, nuclear, and fortunately, hydrogen. Hydrogen is not new. It used to be considered as an energy carrier to convert all this renewable energy into hydrogen and use hydrogen to carry the energy and then use it for future applications like hydrogen car, convert it back into electricity and things like that. A lot happened recently in hydrogen area. Actually, very recently, last year in October, many things happened. First, Biden administration announced the setup of 7 regional hydrogen hubs with a goal to reduce the cost of green hydrogen to $2 about per pound level. And more interestingly to me is that October 29, 2023, there's an article on CNN talking about the discovery of white hydrogen underground. This is very new because people originally thought that hydrogen cannot be found underground. But recently, this concept of geological hydrogen somebody called it brown hydrogen, somebody called it white hydrogen. It's becoming a really, really interesting topic. And the amount of hydrogen people expect to discover underground is so large that somebody say that it can power our society for another 500 years. Okay. So as a result, this become one of the science breakthrough of the year finalists. It's not finally choosing to be the breakthrough of the year. Actually, the weight loss drug was choosing to be the one, but it was the second runner-up for the discovery of white hydrogen as the breakthrough of the year in 2023. Okay, so hydrogen is not only a energy carrier anymore, it's also a energy source. Where it's coming from, well, people have different theories. One of the theories that it came from the reaction between the water leaked into the core of Earth with the iron 3 plus underground, iron 2 plus in underground, and to react with water to form hydrogen. Okay. One of the biggest problems of hydrogen, because we have studied it for many, many years, is hydrogen is so light that it's very difficult to store it and to move it around. The cost of moving hydrogen sometimes is so high that make it economically not feasible to use hydrogen as a fuel. To solve this problem, here is a new concept. So can we react hydrogen with captured carbon dioxide? It's very cheap green hydrogen or white hydrogen and carbon dioxide from the environment so that we can form a liquid fuel with carbon in it. If you burn this fuel, you actually generate carbon dioxide. But originally, this carbon dioxide are from the environment. So the emission from this green fuel, the net emission is zero. Okay. And also, we can use hydrogen and carbon dioxide to make this green daily items. I'll talk a little bit more about that. Is this even possible? I would say that it is very possible because my research and a lot of other people's research, so we can use hydrogen and carbon dioxide to react with each other, either make a carbon monoxide plus more hydrogen and go through a Fischer-Tropsch process to make gasoline, olefin, and a lot of other chemicals. Or like what happened in my lab, we can use hydrogen and carbon dioxide powered by sunlight. We can make methane. Methane can then become methanol and other liquid. So there are ways to convert carbon dioxide captured from the environment and hydrogen to really make liquid fuel that can, have zero net carbon emission when you use it as a fuel. More importantly, we can move beyond the fuel. So the process of starting with carbon dioxide and hydrogen not only can make a fuel, it can make almost everything that currently can be made from oil and natural gas. For example, here the least from DOE side, you can make lipstick, you can make shampoo, you can make umbrella. So many of the daily products we are using can be made from hydrogen and carbon dioxide. So you can think of this chemical process as a way to store hydrogen, to convert it into a fuel and move it around more easily, more cheaply, more economically. Or you can consider this as a carbon dioxide fixation, so that we can make daily product and use it, and carbon dioxide are being converted into a useful product. So that's quite I would think that this general approach can be very, very impactful for the future of our society. Okay, what can we do? We can do research to identify what are the most feasible paths for convert hydrogen and carbon dioxide in liquid fuel. Should we do it in the ammonia path, a methane path, gasoline path, or methanol path? Which one actually is more economical? We can also work on each step of the conversion using renewable energy like sunlight, and to reduce the total carbon footprint. Because if you need electricity to convert hydrogen and carbon dioxide into liquid fuel, the energy you consume still have carbon footprint, even though you are starting material from the environment. But any watt of energy you still has a carbon footprint. So we can do research to reduce the total carbon footprint of our kind of product. What make Duke unique? We have a lot of people. We have a very unique group of people working on related topics. For example, my research on photo-powered harmonic catalysis, Professor David Misi's work on solar energy conversion, Professor Fang Liang's work on carbon dioxide capture, Professor Ben Wiley's research on the commercialization and production of the green hydrogen, and also Echeverry's work on the overall evaluation of carbon footprint and energy consumption. And also Duke has very good international visibility. We have campus in China, campus in Singapore. We can work with people from other countries and really make the impact international rather than just with the US. And Duke really emphasized on the interdisciplinary collaboration and the Nuclear Institute for Energy Environment Sustainability there. And we have material initiative that's also bring people together to work on related topics. More specifically, what I'm doing right now is I'm working with DKU to form a joint research center on green fuel. So I'll work with colleagues at DKU to collaborate not only on the research side, but also on the educational side, and explore the what are the activities we can do between US and China, and how can we work together to enhance the awareness of the climate change. This is a topic that US and China has agreed to work on closely, because it's very simple. If you save the climate on half of the Earth, it's not going to work for all of us. And this is all my presentation, and thanks for your time. And I'll pass it back to Christy.
Thank you, Jay. Just one quick question before we transition over to Lincoln. So you mentioned that in 2023, it was a big breakout year for discovery of geologic hydrogen. Are there concentrated places where this is being found, certain conditions where it's more likely to be found, or is a lot of that information still to come?
People are developing theories behind it. Actually, if you read the news on CNN, one way to discover hydrogen is to have pictures of Earth and see where there is a big area, a round area with no plantation. Because hydrogen can leak from underground slowly, and that prevented the plant from growing. If you see a empty circle on Earth from the airplane or from satellite, very likely you can find hydrogen underground. It's a very fascinating story, and I would recommend everybody read that article.
Awesome. And I'm sure there's some overlaps from the many years of work in geothermal. So I will now pass it off to Lincoln to share his research on that topic.
I want to say thanks to everyone, particularly Christine and Ann, but also to all the Duke alum joining us. I'm not going to be talking so much about my own research on geothermal energy, though I'm happy to answer questions on that. I want to kind of instead focus on what I think is a very interesting sort of rapid development in a particular area of geothermal energy that has some really interesting implications for clean energy development in the US. So some of you may have visited the spot shown in the background of the image. It's the Blue Lagoon in Iceland. The water in the lagoon is supplied by the Svartsengi geothermal power station, the plant in the background with all the steam coming off of it. Iceland gets 27% of its electricity from such plants. What I'm going to do tonight is give you a brief overview of ongoing efforts to develop the same sort of geothermal power capacity here in the US. Let's see. So Jay just discussed the role that hydrogen could play in combating global warming by displacing fossil fuels. Electricity from non-greenhouse gas emitting forms of energy are an equally potent transformation agent. This is because so many end uses of energy that currently run on fossil fuels can be run instead on electricity. In fact, the shift is already underway. The most evident example is what's been happening in the transportation sector, where the internal combustion engine vehicles are being replaced by hybrid or fully electric vehicles. Technologies in buildings and industry, however, are also being electrified, such as furnaces, water heaters, heat pumps, induction stoves, and timed appliances. Powered by clean electricity, these changes will not only lower emissions, but result in more efficient and flexible energy use, which could ultimately also lower energy costs. End-use electrification, however, will raise the overall demand for low-carbon electricity, particularly when coupled with increasing computational demands for power from AI, crypto, and big data analysis. The principal sources for such electricity here in the US now and for the near future are natural gas and renewables. And among the renewables, the biggest sources are wind and solar. Note that the latter, wind and solar, dwarf the power produced from geothermal energy, that dark brown line in the box to the right there. This geothermal energy power production is projected to remain flat over the next several years. So you may be asking, why am I even talking about geothermal? It's because wind and solar have drawbacks as well as benefits as sources of clean electricity. The biggest pluses are that they're mature technologies that are increasingly cost competitive with fossil fuel power plants, particularly wind. The biggest minuses are that wind and solar are intermittent producers of power. They are land intensive and they require critical minerals to be manufactured. Of these three drawbacks, the critical mineral dependency may be the biggest. That's because there remains plenty of land to site wind and solar farms, and the intermittency of these generators can be dealt with through grid operations and energy storage, such as lithium-ion batteries. Critical minerals, on the other hand, are supplied by an extractive industry that can disturb and pollute the environment. There's a global rush to secure these minerals. They are largely concentrated in a handful of countries. And the processes for converting these minerals into metals that go into manufacturing not only wind and solar systems, but also the batteries used to smooth out the intermittent power production from these technologies are largely controlled by one country, China. In fact, at present, China manufactures greater than 90% of all wind turbines, solar panels, lithium-ion batteries, and now EVs, making the production of these technologies far more concentrated regionally than the production of oil and gas. What makes geothermal energy so attractive is that it has benefits where wind and solar have weaknesses, plus some additional benefits as well. Geothermal energy is firm, meaning that it's available on demand. The resource potential is very large, something I'll make clear momentarily. A geothermal power system requires 5 to 10 times less land area than solar or wind, respectively, and the systems require little, if any, critical metals. There is large and skilled ready workforce as well as supply chain for geothermal energy in the oil and gas industry, and geothermal energy systems can be used to store energy, as Jay was talking about. The biggest drawback to geothermal power production is that the resources for conventional geothermal energy production are limited in the US, while the unconventional resources are costly to develop. This figure shows the difference between conventional and unconventional geothermal resources. A conventional resource, also known as a hydrothermal resource, is shown on the left. It involves a subsurface reservoir of pressurized hot water heated by the hot rock of a cooling magma body. When tapped into by a production well, the water flashes into steam and can be used to generate electricity in the same way a coal, natural gas, or nuclear plant does. In the process, the steam cools back into water that is then returned to the reservoir down an injection well, where it is heated once again and can be reused. An unconventional geothermal resource are what are shown on the right. This type of resource has no subsurface water reservoir, only hot rock. In this setting, the water must be supplied. The water is injected down into the hot rock where it is heated and pressurized. It is then pumped back up to where it can be flashed into steam to drive an electric generator. Of the two types of unconventional or next generation geothermal systems shown in this slide, the middle one, the Enhanced Geothermal Systems, or EGS, is furthest along in development. Note that EGS is an open loop system. The injected water is heated as it moves from the injection well through a system of natural and/or man-made fractures to the production well. The total resource potential for conventional hydrothermal systems, the system on the left, in the U.S. is estimated to be about 40 gigawatts, or about 40% of the capacity of the nation's operating nuclear power plants. By contrast, the resource potential for EGS is greater than 4,000 times larger than the 1,300 gigawatts of total capacity of all power plants in the U.S. Again, the drawback to EGS is that it's very expensive. The cost of generating electricity using these systems runs 15 times or more that of onshore wind or utility scale solar. The biggest expense in EGS is drilling the exploration, injection, and production wells. This is because, unlike oil and gas wells, the rock being drilled through for geothermal energy is very hard, slowing the drilling rate and rapidly wearing out the drilling equipment. The U.S. Department of Energy, or DOE, is supporting research and technology development to reduce these and other EGS costs to the point that EGS ends up being about 2/3 more than the cost of solar and wind. Much of this research is being done at the DOE's Forge site in southwest Utah. Here, innovations in drilling technology and operations have resulted in a 5-fold increase in drilling rates since 2017. While still more than 2 times slower than the rate at which oil and gas wells are drilled, the improvements have resulted in significant cost reductions. The DOE estimates that this and other improvements already achieved at Forge will reduce the base capital cost for EGS by almost half. Furthermore, the agency projects that additional innovations being developed at Forge will reduce the capital cost another 33% by 2030. At this point, the DOE anticipates that EGS will be inexpensive enough that when combined with its benefits, investors and developers will begin deploying the systems. The lessons learned through such early deployments are then expected to result in the identification of further cost savings, much like they have for wind and solar. The DOE's end goal is to help promote an expansion of geothermal energy here in the U.S. from a current total generation capacity of 4 gigawatts to 100 gigawatts or more by 2050. Of course, a lot of challenges remain. Like other forms of renewable energy, EGS will have high upfront costs and risks, particularly in the early stages of deployment. There will also be perceived and actual operational risks, meaning that the systems may not initially produce the amount of energy as expected, something that happened with wind and solar as well. And there will be a risk from delays in connecting such systems into the grid, an important challenge that Tyler is going to speak to next. I will end, though, with this slide, which shows U.S. production of oil in brown and natural gas in blue since the 1970s. I'm sure some of you can remember that as recently as 2005, the U.S. was importing over 16% of the natural gas it consumed and more than 60% of its crude oil consumption. All that started to change 3 years later in 2008, when the use of fracking and directional drilling began to successfully unlock vast amounts of oil and gas from what were, until then, unconventional reserves of oil and gas in shale formations. What's generally not known is that the geologist named George P. Mitchell, the acknowledged father of the shale revolution, first began experimenting with fracking shale for gas back in the 1980s. Within 20 years, his effort revolutionized the oil and gas industry and reversed U.S. energy security. There are a lot of parallels between that transformation and the one that the DOE and others are trying to bring about with geothermal energy, though this latter transformation is involving a lot more money and a lot more players. So keep your eye on EGS, because if it becomes competitive, it could be a game changer.
Thank you so much, Lincoln. That was really interesting. And so one clarification here on EGS. we're actually, as you know, but for our alumni, there's research on campus right now for enhanced geothermal, conducted by another professor here in geology at Duke. And what I've learned about EGS is that there's a lot of great applications for building heating and cooling. Do you expect that the applications for EGS will extend to electricity generation fairly seamlessly, or will there be barriers to getting it to perform in an application that conventional has typically provided?
Okay, so it sounds like there's a couple of points to your question there. So you're right, you can use geothermal for heating, and that's one of the things that they're exploring with the well being drilled here on campus. When it comes to power generation, the use of enhanced geothermal energy has the key thing here is that there are a lot more sites across the United States as well as across other nations where EGS could be applied. You don't need that superheated subsurface reservoir. And so you're just basically supplying the water. So I think the technology, although it's still under development, is going to be successful. They've already got PPAs, power purchase agreements for EGS systems at a number of sites around the U.S. These are for essentially systems that will be coming online, projected to come online in the next 5 years or so. So it's definitely anticipated that this will happen. Initially, they'll be small, just, maybe they think they're projecting for 2030, something on the order of somewhere between 5 and 10 gigawatts of new power generation, but then grow it almost, 5 times that by 2050. So I think one of the big issues for geothermal is going to be, in terms of its adoption here in the United States, will be the same thing that's holding up a lot of renewable energy that Tyler's going to talk about, which is linking it into the grid.
Yeah, absolutely. And without jumping ahead too much on the transmission question, I'll punt it over to you, Jay. And I think this pertains to both of these technologies, but we're obviously seeing this rapid transformation to add renewables, add batteries to the grid. We're also seeing headlines about how, as Lincoln mentioned, there's this rapid deployment of data centers, increasing electrification, and even Georgia just approved a slew of fossil generation in order to keep up with demand. So, Jay, for hydrogen, what do you see as kind of the key catalysts or the key things that need to happen so that this technology can keep up with this increasing demand for electricity?
Very good question. I think first we need to find enough hydrogen or generate enough hydrogen, that can power the power plants. So Biden's new regional center, once they are fully functional and producing a lot, the amount of hydrogen that meet our need is that the skill is the first thing that need to happen. The second would be the cost. Because currently natural gas is available and so cheap. I mean, the green methane that made from hydrogen and carbon dioxide for a while will be more expensive than the natural gas you get from underground. How can you prevent people? How can you, I wouldn't call it force, how can you convince people not to dig up the fossil fuel and natural gas and instead use this green alternative? It's the biggest challenge I would say facing us. Must be something to do with education, something from the government side. I mean, forcing people not to use it not going to work. You have to have a way to convince them to stop using fossil fuel. and the natural gas. Yes.
And so really breaking down those cost barriers is the way to do that.
Cost barrier and the education, like if the cost difference is just one time, 50 cents versus $1, maybe you can convince people to do it. But if it's $1 versus like $20, it's going to be very, very difficult.
Yeah. And so speaking of cost, we've got a question from our audience, or actually this isn't related to cost, but a question for you, Lincoln, around the lifespan of geothermal wells. Is that something where, like with fossil wells, they're going to be drying up in any way, or is that heat just kind of constantly available and never degrading?
It really depends on the site. So I'll give you an example being Iceland. I mean, Iceland sits on top of a giant magma chamber. And so that heat is not going anywhere. And those plants will run as long as the infrastructure can, be maintained. The geysers in Northern California sit over a very hot rock, and they've been around since the 70s. That's one of the largest geothermal plants in the United States. In sites where the temperatures are cooler, you can generate power at temperatures as subsurface temperatures as low as 100 degrees Celsius. But so typically you want to be at least almost up to 150 degrees. At those sites, the wells will essentially cool over the course of geothermal energy production if they're run 24/7 over a period of 18 to 20 years. And so you would have to go drill another well at that site to continue the generation.
Got it. Another question for you, Lincoln, and then I'll wrap up with a question for Jay, and then we'll pass it to Tyler. Any risks, Lincoln, of triggering earthquakes from geothermal drilling?
Yeah, that's definitely a concern, particularly when it comes to enhanced geothermal systems. Because you've got an injection well and a production well, and they're connected by a fracture network that is either a natural fracture network or was human-made by essentially fracking the rock. And whenever you pump fluid down through fractures, you kind of lower the friction that are keeping the rocks pinned against that fracture, and you can trigger earthquakes. And they ran into that problem when they were trying to develop one of these systems in Basel, Switzerland, where earthquakes were generated along those lines. So this is a big issue for development of EGS moving forward. And the DOE at that Ford site has a number of seismometers around that are measuring how the fracking and the cycling of water through the system is affecting the seismicity of the region. So definitely an issue that could be a factor.
Got it. All right, Jay, one other quick question for you. So could you clarify, we have a question from the audience, if we can use captured CO2 from carbon sequestration storage to combine with white hydrogen to produce fuel?
Yes, I think that's possible. That's highly possible. Right now it's still costly. We are still working on to reduce the total cost, not only the money cost, but energy cost. But even using current technology is doable. Actually, one example is South Africa, where all their gasoline were made from coal and water. So carbon plus water, we can do the same with CO2 plus hydrogen, because it's just a different ratio of hydrogen and oxygen and carbon in the mixture. So it's doable. It's definitely doable. Really, I would say is that we need to work on the each step in the conversion to reduce the total energy cost, and also to reduce the cost of carbon capture, reduce the cost of hydrogen production and or mining.
Excellent. Thank you for the audience questions so far. They've been great. Keep them coming. With that, I'm going to pass it over to Tyler to start talking to us about grid modernization.
Thanks so much. Nice to be with you all this evening. And thanks so much to the Forever Learning Institute for hosting us. Today, we'll talk about some ongoing opportunities to accelerate our transition to this clean energy future that we've talked a bit about today. And so maybe to start, though, I want you to imagine that you get to the airport and all you want to do is get on your plane and take off and get to your destination. You get in the security line and you start waiting, and 15 minutes passes, and then a half hour, and then an hour, and then actually that ends up extending into a day, and then a week, and then a month, and then a year, and then actually it ends up extending as long as 5 years. And that's somewhat analogous to what's happening to a very, very large number of renewable energy projects and storage projects that are ready to go to plug into the grid, but can't access it due to a variety of factors that are preventing them from interconnecting to our transmission and distribution system in order to supply clean energy. And so what we're seeing all across the country is an explosion in the size of these lines, or what we formerly call queues or interconnection queues, across electricity markets in the US. And so this chart is hot off the press from Lawrence Berkeley National Laboratory with the latest update on the size of these queues. And you can see how much it has grown since the 2017 and 2018 timeframe. And to give you a sense of just how large this is, so the current volume is now on the order of 2,500 gigawatts of proposed projects that want to interconnect to the transmission and distribution system. The entire volume of existing generation capacity for the whole US power sector is approximately 1,200 gigawatts. So in other words, there's 2 times more electrical generation capacity that wants to connect to the system, but cannot do so for various reasons. And the largest portion of these projects, as you can see here, it's primarily solar, battery storage, and wind power projects. There is some amount of gas you can see there, although you can also see how the gas volume in queues has declined actually since the mid-2010s. And then there are a few other resources, but the vast majority, as you can see, are solar, storage, and wind. And there are a lot of reasons for that, but the simplest is that the cost of these technologies has declined very far. They become highly competitive, and of course, there's a lot of demand increasingly for clean electricity from large buyers and also from policy factors. So, what is actually going on when we talk about this process? So we call it the generator interconnection process, and on a standard basis, it's 18 to 36 months approximately, but you as a generator will submit an interconnection request, you'll post some money, you'll be assigned a place in the line or the queue, and then you start to go through these very, very rigorous what are called system impact studies to look at the potential impact of your project on the grid. And then you'll get some results from that. You'll post another deposit. You'll go through another study, which is called an interconnection facility study. And then you'll face a go, no go decision as a project. And at that point, if you decide to proceed, you'll have to execute a definitive contractual agreement called an interconnection agreement. And then you'll post many millions of dollars to cover the cost of any upgrades that have been identified for your project. So we've designed this very, very extensive system to assess the impact of projects on the grid in order to determine whether we're going to allow them to connect. And what often happens because of the way we've designed this system is that these studies will identify very significant upgrades that have to occur to the grid to accommodate the new generation capacity. And there's a lot to say about this, but the basic dynamic is that we have a very, very conservative posture in the way that we study these projects in such a way that we often identify very, very expensive grid upgrades that are ostensibly necessary for them to interconnect. And this becomes a big challenge because generally 100% of those costs get allocated to those projects, and they can only connect to the grid if they pay upfront for all of those costs. So that's part of the challenge, and so we have seen these costs increase incrementally over time across almost every U.S. electricity market. And so there's a lot sort of going on here, but the basic takeaway is that these costs have grown consistently, and that is a barrier to getting the projects connected. And we've also seen the timelines that it's taking to study the projects grow. And so you can see, in particular, since the mid 2010s, those timelines have continually grown. So that's the challenge we're facing. The good news is that we have some really clear success stories that have emerged that are sort of pointing the direction to a new way that will hopefully unlock this bottleneck and allow more of these projects to connect. And so the clearest success story is actually in Texas, which is fascinating, of course, because Texas doesn't have any particular decarbonization standard or even pro-renewable policies. They just said they provide very open access to their electricity market, and they make permitting very very simple, and they provide for a very streamlined interconnection system that allows these projects to connect to the grid much more quickly and at much lower cost. And so this is one illustration of the results. What we're seeing, and ERCOT is Texas's electricity market, is that Texas is interconnecting much more capacity than any other electricity market in the United States right now. And so we at the Nicholas School and a few others have sort of dug into this to sort of figure out what's going on and why Texas is succeeding, but just also illustrate it in another way. So some of you that have visited North Carolina recently, you may have known that North Carolina was number 2 in the country for installed solar, utility scale solar in particular, for actually several years. And so you can see in this chart that in 2018 and 2019, North Carolina was still number 2. But then starting in 2020, you can see that Texas really started to emerge as a new leader. And then since then has really blown us out of the water and a lot of other states substantially because of their ability to interconnect these projects more quickly. And this approach for ERCOT, this has been really important, not only in of course decarbonizing their grid, but actually in helping them to provide more reliable power to their customers. And so their peak demand for electricity has been growing quite quickly in the past few years. And if it wasn't for their ability to interconnect, and it's really been solar that's been the primary addition to their system, if it wasn't for their ability to interconnect all that new solar generation capacity, they may have faced rolling blackouts across their system this past summer when they faced their new sort of record peak demands. So this ability to connect projects more quickly is also arguably really important for ensuring the reliability of the electric power system, especially in the face of rising demand for electricity from data centers and electric vehicles. And new factories and electrification of other devices. And so this is some of the research that we at the Nicholas School have already conducted on this. This is a white paper that we released last August that we're doing more research on top of right now, but it's generated a lot of interest because it is a very complicated topic, and one that hasn't arguably been sort of sufficiently characterized until the past couple of years. But regulators are very interested. There's been a very strong reception to our research, and we're hoping to keep building on it. And it's been very hopeful to see our regulators and policymakers and the U.S. Department of Energy begin to point point towards this kind of new direction. And so this is a very significant new report that the Energy Department released actually last week, and it's their first ever roadmap for interconnection reform and includes a lot of different recommendations. But a really key theme is very consistent with what we've been discussing here in terms of creating more fast track options to get on the system. And we were very pleased that the roadmap also referenced our paper and some of our research thus far. And so we're hoping to build on this going forward. And the one thing I'll say too is there's a whole other side to this, which is very important. So we not only need to streamline access for this backlog of projects to access the grid, but also we need to think about upgrading the transmission system and distribution system more proactively. And so we've seen momentum in this direction and in certain states and jurisdictions, but it'll be very, very important to continue to modernize both the transmission and distribution system to support these new projects. And there's actually a big new regulatory initiative that the Federal Energy Regulatory Commission is about to launch on this front too. So there's a lot going on. Very exciting. It's a great news story, I think, overall, because we have a lot of clean energy capacity that's ready and willing to supply our system. And if we can just get better at streamlining their access and getting them on the system, we'll be well on our way to decarbonizing the power sector. So thank you.
Thank you so much, Tyler. And so maybe for our first question, we have a question from the audience around technical limitations driving some of these holdups in the interconnection queue and whether high voltage direct current is a solution to mitigate some of those issues. Is that an avenue that the U.S. can consider, and why or why not?
Yeah, really interesting question. I guess to address the first part, there are a lot of aspects specific to the way these studies are conducted that can lead them to identify very expensive upgrades to the system that may arguably not be necessary in the vast majority of likely system conditions. And basically, the way these studies are run, they consider every possible outage of any element on the entire transmission system that could occur, and then they see if this triggers an overload that then would require an upgrade. So there's a lot more depth to go into there, but that's kind of what's going on with this contingency analysis. I do think that there's really, really interesting potential for high voltage DC transmission, and I think that would fit in really well with the sort of proactive transmission planning agenda. And it's going to be very particular to a certain part of the country where you're trying to access new resources that you've identified as being relatively low cost. So to do that, we need that sort of proactive transmission planning effort, which is complementary to this sort of faster grid access for queued projects.
Yep, absolutely. Makes sense. Another question from the audience is around ERCOT's benefits in being a single state grid. So can you talk about how some of the things in the the advantages that ERCOT has, how those can transfer to these ISOs and RTOs that cross multiple states.
Yes, it's a really important point. ERCOT is a different type of market, and one of the reasons they are different is because they are a single state, so they're not subject to most FERC jurisdiction, and so they have this very different sort of market design where they're what we call an energy-only electricity market, and so they don't have what are called capacity markets, or what we call the resource adequacy construct. And so it is a different beast. It's certain other markets, could technically go that direction. I think most of us think it's relatively unlikely. So the task that, and this is part of our research and others that are exploring this, is to figure out how the learnings from ERCOT in Texas can be adapted into these other market frameworks. And there's a lot to say about that, but one is that we can offer an energy only as available interconnection option for projects outside ERCOT. And there are pros and cons of that, but there are certain trends in the power sector that suggest that a lot of projects increasingly would be willing to go that direction. So hope that's helpful, at least as a snapshot.
Yeah, absolutely. And I want to take a moment to kind of tie the topics that we've been discussing today to transmission and the grid. So, how, and this is a question for anyone, any of our speakers, as these more emerging technologies or kind of emerging commercial technologies such as geothermal and, say, hydrogen for electricity become available, how might that hinder reforms for ISOs and RTOs to get more electricity off the ground?
I'm not sure what you mean by hinder, but I would say one of the things that's interesting about geothermal, I mentioned that you can use it also as storage. Most geothermal plants are run like baseload plants, meaning that they're run 24/7. They have what are referred to as high capacity factors. They run all the time. But it turns out that they seem to be fine to run as load following plants, meaning that you can ramp up the power output from geothermal as demand rises and then lower it as demand falls. And you can even, for example, stop producing, keep the heat underground while solar is generating power, and then as solar comes off, bring geothermal on. So they can act like a lithium-ion battery storage system, but you're doing it with a natural process. So in that sense, geothermal could help the ISOs by serving as both a flexible generator and a baseload generator.
On the same line, hydrogen can also be a good energy storage media. So basically, when you have too much energy from solar, from wind that you cannot use, you spirit water to make hydrogen, and then you store it in a way of hydrogen or convert it into ammonia, methanol, methane, and then you actually use it as a fuel to generate the power when you have higher demand of energy. So people in California talk about using hydrogen as a kind of a storage media to to help the solar industry.
And I guess to kind of tie that back to you, Tyler, I guess the question I'm trying to get at is, are our grid operators prepared and equipped to be evaluating these increasingly diversified projects as they've historically been already facing a lot of backlogs with solar and wind, and now there's just an increasingly diversified resource mix?
I think because of these pressures, they're getting much more efficient, and there are already improvements that are happening. There was a a very significant new rule released by the Federal Energy Regulatory Commission on this very issue last July, and it doesn't solve all the issues, but it is an important step. And so, of course, all of the electricity markets and transmission providers are very well aware of this issue. So, I think all the process improvements that they make today and in the years to come, that'll make them much better prepared if there's another wave of other resource types. So I think we're in this very sort of unique pinch period where we really have seen a kind of frankly a revolution occur in these technologies that we've just never seen anything like this. And so there's growing pains, and but we'll work through it like we do with anything else.
Excellent. Well, I'm being told that we are at time. So as we wrap up, I just want to take one more opportunity to thank all of our speakers for joining us today. After having had the opportunity to learn both from Lincoln and Tyler as a student here at Duke, it's been a pleasure to dig deeper with both of you into your areas of expertise. And Jay, now I'm wishing I had another semester to learn as a student from you about your work. And then again, thank you to our audience for all of your insightful questions. Apologies that we couldn't get to them all tonight, but it was really interesting to hear your thoughts on these topics as well.